Welcome students. We are now available and sitting together for the next module of our Hypersonic Aerodynamics course, and this time we are going to take up a very small topic in this particular course, that is called hypersonic flight path. As a matter of fact, the hypersonic flight path has nothing to do much with the hypersonic aerodynamics, because it has more to do with the vehicle mechanics and the vehicle dynamics rather than fluid mechanics. But still, this has been kept in this particular topic, in the particular subject, because after all, this entire aerodynamics is going to be applied in the vehicle dynamics itself, and then we have to finally calculate, estimate and design the performance of the vehicle. So let us start now and see how it goes ahead. This has been this is a very small topic related to your hypersonic aerodynamics. What is flight path? Very simple question to ask. What is flight path? Actually, the hypersonic flight path basically the velocity altitude map, because it deals with the velocity changes as the velocity attains altitude or loses the altitude, and that is the subject matter of this particular topic. After this the little discussion, we'll also like to see a small velocity map, velocity altitude map, and we like to have little discussion on that, and we'll see that how actually this hypersonic flight is actually structured in this velocity altitude map, and we'll try to also learn the salient features from that particular map. Let us just start acting on the velocity altitude map. Before that, we have to before actually we have the map, we must have the equations. So let us see the equations first. As we derive any vehicle dynamics equation by simply drawing the free body diagram, here also we are going the similar way. We have one hypersonic vehicle coming down with the negative angle of attack. The angle of attack taken negative is because the vehicle normally attains the hypersonic velocity, or during re-entry. So it is actually coming down, normally does it. We can actually attain that altitude, hypersonic regime also by in the ascending flight, but that will normally cause a very huge amount of power required from the engine, from the propulsion system. So in normal cases, a vehicle normally attains the hypersonic velocity when it actually during re-entry in the Earth atmosphere, when it is actually going towards the Earth. So it is actually descending. It's not a ascending flight, it's a descending flight. So we have taken a simple case of a descending vehicle, and all the forces acting on this have been depicted. This is the lift, which is perpendicular to the flight path, and this is the drag, which is acting opposite to the flight path, and this is the weight acting downward, and this r is actually the radius of curvature. So it r tells a non-zero r will give an idea that this flight path is not straight and it is actually a curved. So r is basically a radius of curvature of the flight path at a particular location. It will change from location to location, but any particular location, if r is the flight path radius of curvature, so it is given like this. And v is the free v infinity is the free stream velocity at which the vehicle is descending or moving forward ahead. One thing it has to be marked here is that we don't have any thrust acting here, because since it is gliding flight or since it is diving flight, we don't need the thrust to act. In fact, we need more and more drag, so that the vehicle can dive with a slower speed, and it can be easily controlled, and then the impact with which it will land on the surface will be smaller. So just keep this picture in mind, and then we'll just try to derive the equations. Picture is available here also anyway. So this is writing these two equations we can easily write by writing the force momentum change conservation, and I can say the Newton's second law of motion in along the flight path and perpendicular to the flight path. So this equation w sin theta minus d, this m dv by dt, is actually talking about that the motion along the flight path, and the equation 2 is talking about the forces acting uh, in the flight path perpendicular to the flight path. So L and W cos theta and R, this is the centrifugal force acting. In fact, we could have put this thing this side and put this negative sign this side, but we just want to keep this acceleration term in one side, or all the forces acting in one side. So in this case, the force acting in the flight path direction is actually the one component, the sine component of the weight, and then the drag is just opposite, and then we have some kind of if deceleration is there or acceleration there, whatever maybe, we can write this thing m dv by dt. Similarly, we are having this L minus W cos theta into minus mv square by r, that is your centrifugal force. So on rearranging, we just rearrange like this thing. Now we after these two equations, we put an assumption that theta is very small. If theta is small, then we know that sin theta is equal to actually theta, and cos theta is equal to 1. And if theta is really very small, then sin theta can be taken as 0 also. It's 0. So sin theta is 0. So this term vanishes, and this term becomes 1. So now if this term vanishes, it becomes minus d w by g. W by g is actually m by v. M is equal to w by g, and then we have this L minus w, so cos theta becomes 1, sin theta becomes 0, and then we put this thing here. There is not much manipulation in these two equations, but just by putting the assumption that theta is equal to theta is very small, and then sin theta is almost vanishing, so we put 0, and cos theta is equal to 1, we get these equations. Now applying the equation for the lift and drag, this is the common equation. We know this thing, lift is equal to this, and dynamic pressure, and then coefficient of lift, and the surface area. Similarly, the drag is equal to that dynamic pressure, then coefficient of drag, and the surface area. So the lift and drag are defined this way, and this are actually put in the previous equation. So we get these equations, and after little manipulation, we just find that we separate out this parameter. We have to make sure that this parameter is negative. This coming, this to CD by CDS by W is coming, to write it opposite way for some different reason. So this parameter W by CDS or W by CLS are actually our some special parameters which we are going to use, and we write it in this way. If it is coming reciprocal, then we just put the sign -1, but we write these two parameters always in this fashion, because these are special parameters for us. What are these parameters actually? Let's see. So one is parameter here, other is here. So if you recall, we discussed while talking about various types of vehicle in the flying with the hypersonic regime, we talked about two design parameters. One is the ballistic parameter, and other is the lifting parameter. The ballistic parameter is found by writing the momentum equation in the flight path direction, and the lifting parameter is found by writing the same momentum equation along the perpendicular to the flight path direction. So by going these two equations, we find that this is nothing but the ballistic parameter, and this is the lifting parameter. So we have ballistic parameter, we have the lifting parameter here, and always remember that in the lifting parameter we have this CL, and ballistic parameter talk about CD. So for purely ballistic entry, suppose during re-entry, the vehicle is designed to re-enter with a purely ballistic type of re-entry. In that case, the ballistic parameter becomes very important. We have to take care of this design very carefully, and CL by this lifting parameter is not that important. So we can actually anyway that some kind of compromising is possible. But in the case of purely lifting entry, the lifting parameter becomes more important, obviously, and the ballistic parameter can be ignored if it is giving some difficulty. Let us just see some vehicles which are actually having some these kind of things. So students can actually recall this, that this is the Apollo capsule, moon landing capsule. After the landing and doing all the missions, when the astronauts were returning to the Earth, they came in this capsule, and this entered in the Earth's atmosphere with a very high Mach number, something like 36 Mach number, perhaps 36, and this is the highest Mach number people have achieved till now in the flight. And this is entering with a purely ballistic type of force acting on this. So it is actually a ballistic entry. See that the flight path is completely faced almost perpendicular to the surface. So the very high angle of attack will be there, and this will actually give a huge drag, and that drag will try to slow down the vehicle. That's what is expected, because it doesn't have any wings, so it will actually it will not be able to control. Finally, it has to land with the parachute, and parachute cannot be deployed at such a high velocity and such a high altitude. So the ballistic impact is actually used to slow down the vehicle. So this type of entry are termed as falling under the category of ballistic entry. Next one is, there is another vehicle which is just fired from here, and then finally it start landing. It looks like it has some wings, and it looks like it is something like it's a plane kind of thing, or hypersonic plane, but this also is actually a ballistic re-entry. After that, it enters with a ballistic type of re-entry it is making, and finally it is landing here. Ballistic type of re-entry doesn't mean that it should not have wing. Try to understand first thing, because in the case of ballistic entry, the maximum surface area should be faced in the flight path. So that gives the highest angle of attack, and that also gives the highest drag. That is required. So a huge drag is acting in the flight path direction and opposite to it, and then it helps in actually slowing down. So this we are actually encountering in this type of entry also. This is also a ballistic entry. So this in this kind of design, ballistic parameter will be more important. Next one is, again, this is something confusing, because this is the space shuttle of NASA space shuttle, and this is having wings, and this creates lift also. So by looking, it looks like this is a making a lifting a type of entry. Lifting parameter is more important for this, but no, this is also a ballistic entry. If you can recall the entry of the moon Apollo capsule, this is also having the same thing. The maximum area, the surface area, is actually faced by the flight path and direction. So the flight path direction is falling normal to this maximum area. It is almost same. It doesn't matter whether it is upper surface is something like going in the smooth manner like a capsule. This is also facing maximum area. It is going in the ballistic manner. So right now what is facing is actually it's also a ballistic parameter. It's also a ballistic entry. A little bit of lifting parameter is also important here, because it has wings, and if the angle of attack is not exactly 90 degree, then definitely some kind of lift will be generated, and that lift can also be accounted here. So this is also a ballistic entry. Here is giving the two differences between the ballistic entry as well as the lifting entry. The ballistic entry normally that comes down faster, something like acceleration is something like more than 8g, and then also it comes down narrower. It doesn't travel more distances. The reason is it doesn't remain in the air for a longer duration. While in the case of lifting entry, it is its angle of attack is also a little bit smaller. So it not only falls down with a smaller speed, this also actually travels and starts covering the more speed than the ballistic entry, ballistic type of entry. And also for the lifting entry, again, it's not very necessary that we should have a wing. So so the students should be very much careful about it. All the angle of attack and design of the entire mission determines whether it is lifting entry or the ballistic entry. And anyway, the vehicle shown on the in the picture, both are actually having no wings, but it can make the ballistic entry as well as lifting entry. Of course, if it doesn't have wing, it cannot be controlled, and it cannot fly like airplane. So this has to have some kind of it should land with the help of parachute to ensure a least impact while touchdown. This is one of the vehicle. This is which tries to make the maximum of the uh, lifting entry, and the lifting parameters become more important for it than the ballistic parameter. One more vehicle which is I'll show that, which is purely lifting, which is purely lifting parameter. So it makes a purely lifting entry, and this kind of vehicles are normally are actually going, this is actually going, and they just ascend and then descend. So they go up first, and during re-entry they attain the hypersonic speed, and at that time you can see that the body itself is telling that it actually it will fly by using its wings. When it flies by using its wings, it will actually also travel a larger distance, and this kind of vehicles will make the a lifting entry. One thing we have to be we can care here, and we can just point out here that during the ballistic entry, the people while sitting inside don't have much control of the vehicle. Even if the vehicle has wings and lift and flaps, that will not be very useful, because at that high speed, if you try to deploy it, it's definitely going to break down the structure. So basically you try to dive as fast as possible, and then actually they use the air friction drag to slow down. Once the velocity comes within the limit, they start actually controlling the vehicle. In the case of lifting entry, the speed is not very much, and something like the most famous ballistic entry, which is we know right now, the ballistic entry made by the capsule of the Apollo mission. So that is completely blunt, and then it doesn't have any wing. Now that type of high Mach number may not be achieved by this vehicle, but this vehicle still can go to the supersonic Mach number and hypersonic Mach number, and it during re-entry still it can be controlled. So it will not have a nose dive kind of thing. It is actually manned mission, and man has to control this and let's make a safe landing. So they will go. It will go like a regular mission, going in the space and coming back. So regular mission will be done, and they will have all this control and control surfaces, and they will try to actually control the vehicle using them, and that type of entry will be termed as lifting entry, because the lifting surfaces will be applicable here, and then it will actually try to maintain some not very high angle of attack, but some low angle of attack, where you can get actually huge or a very high lifting parameter. We saw already W by CL by S, and that lifting parameter, and that will be important in controlling the flight path. So this is one of the vehicle which actually makes purely re-entry, purely lifting re-entry, and this vehicle we know already. This is NISP. So this is National Aerospace P4 plane. Yes, no, National Aerospace plane. And this is again, as I told you, that X means experimental. So they will not go into production unless they have sufficient data available, and they have made enough analysis, and they know that safety is ensured, that people can go and come down safely. This is still the experimental prototype, and they are just making all this thing, but they are flying successfully perhaps. And then we have this name, National Aerospace plane. It's accent re-entry type of vehicle. It can go in the space and come back. So these are your lifting ballistic parameter and that lifting parameter. These are our important parameters, and with this help of these two parameters, we normally derive the velocity altitude map. So flight path plotted on a graph of altitude versus velocity are called velocity altitude map. So the definition of velocity altitude map is that this is the flight path, nothing but the flight path. So and plotted on a 2D plane, one axis represents the altitude and other represents the velocity. So velocity and altitude are represented, and as the velocity changes, what is the altitude change, that is plotted. That particular map, we call it actually velocity altitude. A common typical velocity altitude map is shown in the picture. You can see that we have, it is actually looking something like a hysteresis curve, if you recall that. So we have this curve goes like this. Initially it penetrates deep down, and then it flattens because it slows down because of friction available on the atmosphere. Then again it actually sharpens, and then finally goes to the zero altitude and zero velocity. The few of the salient features are available in this in the particular map, and that we should always remember. Let me just discuss those things. The first thing is, when the re-entry happens, basically concerning velocity, the vehicle enters with two types of velocity, different types of velocity. One is called satellite velocity. So satellite velocity, when the vehicle re-enters into the Earth atmosphere, and if during re-entry that it sees that actually it comes from the orbit, some of the orbiting some orbit where we actually the satellite goes around the Earth. So if the vehicle is re-entering from the by breaking out from one of the orbit which is around the Earth, then it is called actually the satellite velocity entry, because the vehicle will re-enter into the Earth atmosphere with a velocity which will be equal to a satellite velocity. When suppose one satellite breaks down and starts entering into the Earth's atmosphere and comes down toward the Earth, it will have that particular velocity because it was already going in the with the particular speed it was going inside the on orbit. So satellite velocity entry is that entry which is made from breaking down from the orbit and then coming to the Earth's atmosphere. Other one is escape velocity entry. In the case of escape velocity, entry, when the vehicle breaks down from the at influence of some different planet, a different celestial body, and then it re-enters into the Earth's atmosphere, then we call it escape velocity. By looking into the conservation energy, we can say that these are the velocity which are recovered. These are the velocity with which these vehicles have been projected out of the atmosphere. When you project a satellite with a orbital velocity, it goes in the orbit. So when it breaks down and comes back in the Earth's atmosphere, it regains the same velocity. So this is the called satellite velocity entry. When a vehicle is sent in the outer atmosphere, in the outer space towards some outer celestial body, or maybe Earth, maybe the outer planet, then it has to escape from the Earth's atmosphere, and then it has to be given the escape velocity. While coming back, it regains all its energy, and then it actually enters into the Earth's atmosphere with the same escape velocity. That's why these two entries are having this much difference. Now, one more thing again has to be clear, that actually the escape velocity is normally larger than the satellite velocity. That's very obvious to say. If the satellite gains the escape velocity, it will not go around the Earth. It will escape. It will go somewhere else. So satellite velocity has to be lower than the escape velocity. And satellite velocity is actually the velocity which is required to go in the orbit around the Earth. Now escape velocity also, you can say that something like 35,000 feet per second is actually falling like this thing, somewhat equal to for the Earth's atmosphere. Now second salient feature about this is that the vehicle which are making actually the lifting entry, they are following the curves which are the upper side of this map. Actually these the dark curves are actually the lifting curves, the lifting entry curves, and they are falling on the upper side of the map, and the lower side of the map is actually the ballistic entries. And this is the reason for this is that the moment the lifting entries happen, it will start flattening, because wings are there. It will start traveling. It will create more drag through the wings, and you start actually flattening the curve, and the velocity will start coming down even without losing much altitude. But in the case of ballistic entry, there is no wings contribution. Even if wing is there, the contribution is very, very less. So mostly it slows down by the friction of the Earth's atmosphere. So it takes some time before actually its speed start coming down, and then the curves start flattening. These are the dotted line curves are for the ballistic entry curves. So before it happens, it goes deep down, larger than the lifting entry type of vehicle. So it penetrates deeper little bit, and then it starts flattening down once when the Earth's atmosphere start taking its effect, when the air becomes more dense. Apart from this, one more salient feature we can mention, we can just note it down here, that even for the same type of entry, like lifting entry or talk about ballistic entry, even for the same type of entry, the higher value of lifting parameter or ballistic parameter in both the cases, for the higher value of lifting parameter and the ballistic parameter, the vehicle penetrates down in the inside the atmosphere for a longer distance, for a longer altitude, and then it starts flattening, and then it start actually reducing the speed, and then coming down to the earth. So in the case talk about these two can be compared. Here the lifting parameter is 10 pound per feet square, it is 100 pound per feet square. So this is actually penetrating little bit down deeper from here. It starts flattening here itself, but it goes down and start flattening here. In the case of ballistic entry, the similar thing happens. This has gone down compared to the lifting entry, but it has still not gone down compared to this one. So for a lifting entry of ballistic entry of ballistic parameter 23 pound per feet square, we get a this dotted curve like this. And if it goes for 100 pound per feet square, this goes in this manner actually. So it goes for the higher ballistic entry parameter type of entry, it actually penetrates little bit deeper before the curves start flattening and the velocity start decreasing considerably. And one more thing is very much clear from here. In this region where the vehicle will be not in the hypersonic range, and also it will be very near to the altitude, this point is 0 velocity and 0 altitude. So in this region they start matching. See that. So this is 23 pound per feet square, and this is 110 pound per feet square. They start matching with these two curves because they are very close to each other. The values are very close, and this curve is actually which is actually representing 100 pound per feet square, and this curve is representing 100 pound per feet square again for the ballistic type of parameter. These they start matching again. They match here actually, and when the escape velocity entry happens, normally this happens with the ballistic entry only, because till now we have not observed, and also if even efforts have not been made to make some airplane which is actually which can make a which can make a the lifting entry with the escape velocity. This is a really tough job to do. Until now it has not been actually experienced perhaps. So escape entry is a purely ballistic entry, and when it happens, this quickly goes down deeper because it's actually having very high that ballistic parameter. And this also is having 100 ballistic parameter equal to 100 pound per feet square. So both are falling parallelly. Only thing is this falls at the higher velocity. The reason is escape velocity is larger, but both go almost same. Then again they start catching up. Once they start flattening, they start catching up, and they catch very fast, and they catch much ahead of this thing. Even at 15,000 feet per second, they just meet here as per the this curve available, and then they start actually then they follow the common path. Whether it is satellite entry or this is escape velocity entry, doesn't matter. They follow the common path. So I hope everything is clear from this particular map to the students. Please just visit the websites, and maybe the NASA website will be more useful. And so look into the books also and see that if you want, you can gather the more information about this. And definitely, if you have any confusion, you can ask, and then we can discuss on this thing. Now here is a small example I have put there. The reason for putting this example is the most of the problems will be actually coming from the American books, because they have been dealing all these things. So and they have this units of FPS, foot pound second kind of unit they are following. So when you start dealing with this kind of units, we must be able to must be feeling comfortable to actually convert these units into SI units, and then so that I have given this small example that these units are given here. So how to convert this this unit for this ballistic parameter or maybe the lifting parameter. Both are same. both are having the same units. So to convert this unit into the into SI units, we need to get these equation that conversion factors. 1 pound is equal to 0.454 kg and 1 feet is equal to 0.305 meter. So by using this, we can actually convert from here to here, and this is also something similar to the ballistic the lifting parameter, because CL is there, but only thing is that instead of weight, the mass has been used. So this pound becomes actually the kg here. So this can be converted into this unit can be converted into this unit using this parameter actually. So students should make little practice on this and get familiar with this, and then will be ready for the dealing in any kind of situation in the examination when some parameters are given in the foot pound second unit, and then you have to convert into SI unit and then deal with the situation. Okay, in the next session, we'll just try to learn some of the conservation concepts, and conservation concepts are not unaware or not totally a dark area for anybody, any of us, because we know we have already gone through this kind of concept. We have studied this in the fluid mechanics. We have studied this in some kind of, I think, thermodynamics also. In thermodynamics, we have studied the energy conservation, and then we have studied the same thing in aerodynamics also. So these things we have been dealing for the last 2 to 3 years. So we should be very much aware with this conservation concepts. So, but still we'll try to capture these things a little bit. And apart from this thing, there's one more concept related to conservation concept is available, and which we deal normally in the hypersonic flows, which normally we don't deal in the other regime like supersonic regime or the some kind of subsonic regime. That conservation concept will take a little bit more elaborately in this when we deal with this thing actually. And after that, we'll just go for the shock and expansion waves in the hypersonic flow. It's nothing but the same shocks, because shocks are just the shocks. It's just the higher Mach number they have. The free stream Mach number is higher. So the same shock and expansion wave equations which we dealt with in your something like supersonic flow, we are going to deal with them again by just putting one extra condition, that what happens when the hypersonic when the same waves are generated in the hypersonic regime. So actually when the Mach number is very, very high, in that case how these equations are going to be modified and how they are going to behave. That's what is the subject matter for this particular topic. So see you then in the next class. Until then, enjoy the learning. Goodbye.